Hey guys, these are some notes for forces after we've had a look at the online simulation. So I want you to copy down notes on slides that say copy these notes into your lab book so you've got a copy of them as well. Right, so you would have learned a force in level 1 and year 10 as a push or a pull. I'm now redefining that and having a different definition as an interaction. A force is an interaction between, this is really important, between two objects. So for example, I kick a ball, okay? When my foot is interacting with the ball, there's a force, right? So when it's touching, there's a force. I stand on the ground. At the moment, I'm interacting with the ground, okay? When I'm off the ground, I'm no longer interacting with the ground, so there's no force between me and the ground anymore. So it's really important that it's between two objects. You can't have a force with just one object, and it's an interaction between those objects. So we've got two types of forces that we meet: contact and non-contact. That just means contact means they have to be touching to be a force, and non-contact means that they can apply forces without touching. So it's almost kind of magical. The obvious one for the non-contact is gravity. Gravity, with my picture of a person up here, gravity can pull down on me, and the earth doesn't need, here's the earth underneath me. The earth doesn't need to be touching me to be able to pull on me. So it's a non-contact force. The two types we've got are gravitational force and the electromagnetic force. The contact forces, and these are the only 5 forces we're really going to deal with this year, are, but let's just go back for a second. Electromagnetic force, an example of that is a magnet. And we're going to meet some more later on this year. Contact force is the one that you need to touch for it to happen. Now, the normal force, you might have used to call it support force or reaction force last year. This year, the name I want us to use is normal force. In science, normal means 90 degrees to a surface. Okay, so when I'm standing on this surface, the normal force is 90 degrees. It's this way here. Okay, here's the surface, and here's the 90 degrees, and that's why the normal force goes up. It makes sense because when we start learning about standing on slopes, the normal force is not upwards, it's 90 degrees to the surface. Okay, so normal force is what we're going to start using instead of support force. Friction force, you know about that. Friction opposes motion. There's another type of friction, which is like grip, and the word we use is traction, that assists motion. So friction often slows things down, and traction often helps speed things up. You know, if we want to go running, we want lots of grip on our shoes. So I'm okay if you just call them both friction. If you want to separate them and say, look, in this case it's traction, you can do that. And the last one is tension forces. That's a string or any sort of pulling force is a tension force. We've got 5 forces we're going to deal with this year. It should be that easy. 5 forces. So no, you can't start making up extra forces like acceleration forces and momentum forces and thrust forces and all that kind of jazz. These are the 5 forces. If you can't explain it with these 5 forces, you can't really explain it. The other term we're going to do is net force. Net force means total force, or could be meaning balanced or unbalanced forces. But I like using the term net force. So net means total. And what it is, it's the overall effect of all the forces acting on an object. So if we've got an object here, we've got 20 newtons down and 20 newtons up and 5 newtons to the side. The overall here, these cancel, and we're just left with a net force, in this case, of 5 newtons. The symbol we sometimes use for net force is, I'm going to be very careful when I draw this. It's a big, funny capital E and then F. That means net, or it means total. It's a Greek letter, and this is obviously force. So copy those notes down. If you want to copy my little diagrams, you can. I'd say pause the video now and copy them down before you go on to the next slide. So don't copy this slide because I'm going to do a different take on it in the next one, but this is just explaining first and second law. So the first law, Newton's first law, is if the forces are balanced on an object, that object stays at a constant velocity. And that means it's either moving at a constant velocity or it's not moving. You can have a constant velocity of 0. Newton's second law says that if you have an unbalanced force on an object, this causes acceleration. The reason I didn't want you to copy this slide is the next slide, which I'm going to go to now, I like much better. The same Newton's first and second laws, but I do them in my head whenever I'm thinking about them as this flow chart. So once I finish talking on this one, make sure you copy this down. So I think about, if someone gives me an object and asks me to think about Newton's first or second laws, I say to myself, is it accelerating or is it traveling at a constant velocity? If it's traveling at a constant velocity, or is it accelerating, I'll go down one of these paths. So if it's traveling at a constant velocity, the forces must be balanced. This means the net force is 0. That's just two ways of saying the same thing. This whole path here is Newton's first law. And on the other side, if your object is accelerating, the forces must be unbalanced. And that means that the net force is not 0. Oh, go back. Sorry. Unbalanced, not 0. This whole side here, you guessed it, is Newton's second law. This I take around in my head all the time. And this is the decisions I go through all the time when I'm solving physics problems, this flow chart. So pause the video and copy those notes down. Last one, we want to draw force diagrams. And I want you to be really specific on, well, I want you to be specific on how you draw these force diagrams. So let's say I asked you to draw a force diagram for a cat sitting on a mat. Often they'll give you the diagram in a question, but let's say they didn't. We've got the mat, we've got the cat sitting on the mat. First thing, sketch a diagram, everyone can do that. The second thing is identify what we call the system. The system is just everything we care about. Now in this case, you're drawing a diagram for the cat, and so what we do is we draw it with a dash box. So I identify my system by drawing a dash box around my cat. So system is the things we care about. And often, if there's more than one thing in a system, we simplify it down. We pretend it's one object. I'll give you an example. Say we've got a man and he is he's parachuting, right? In this case, if I told you to, I'd say, well, can you please look at the whole system of both of these together? Then you wouldn't think of the parachute as separate from the man. You'd say the parachute and the man are one thing. Okay? You could have, if I'd asked you to, and we'll look at these down the line a bit more. I could have said, can you look at just the man by himself without the parachute? And then you'd say, okay, this is my system here. So I think I'll be pretty clear on what the system is. And at the moment, you're like, I don't understand why this is important, but you'll start seeing it in a couple of lessons. So identify the system with a dash box. All right, so redraw the system as a dot. I say this because you can't draw cats as good as me. So instead of drawing the cat beside it, you'll say, okay, I've got a dot. Add my force arrows. Now I can draw my force arrows. What's my forces on this cat? Well, I know there's always going to be gravity. And in this case, because he's sitting and if I go back, I don't want to go back, but the page before where I talked about is he going at a constant velocity or is he accelerating? This cat's definitely not moving, which is a constant velocity of 0, so his forces must be balanced. There must be a force upwards. Always draw your forces outwards from the dot. Don't don't draw a dot and then draw your forces in like that. That's bad. All right, label the forces as F-type on A by B. So what that means is you write a big F for force, because we've got so many arrows in physics, we've got to make sure we label them. What type of force is the downwards one? It's gravity. So you can just put G for gravity. If you want to write the whole word out, you can. It's up to you. Then you do comma on A. So on the cat. By what? What caused the gravity on the cat? Well, it was the Earth. Cool. And then I do the other one up here. This is F, N for normal. You can write out the whole word if you want, or you can just leave it like that. I'll just leave it like that so you can see the contrasting. What is it? It's on the cat, and it's by the mat. This may seem tedious, but I really, really want you to make sure that you do the whole names. Don't just write F, G, and leave it like that, or even worse, just write G. Go through this process. I'll start marking you down if you don't. The last thing is add equality arrows if they're needed. So if the forces are equal, you can put in your equal signs to show that they are equal. So there's your force diagrams.